So far, we've been talking about regression, okay? But there is another topic which is logistic regression. Logistic regression is not so much of regression per se, it is more of a classification, okay? But the title includes regression, so we're going to talk about this one in this chapter. Okay, so in the logistic regression, we are interested in categorical variables. So like classification, binary classification. So we're interested in classifying whether this belongs to the first class or second class. But in the linear regression, the output was continuous variable. So is it 0.2 or 0.3 or 0.4 or something? So implicitly, we assume that the continuous variable is Gaussian in the linear regression, but in the logistic regression, the output is Bernoulli distribution. And for logistic regression, we have a sigmoid function, which can be defined in this way. So as I said, we're interested in the probability of the output. So this is the probability of the output when the output is 1, okay, given input x. This one can be simplified by one function, which is a sigmoid function, and this can be defined in this way. And then this z is a linear, or it could be a neural network with the many layers, okay? And sigmoid function looks like this. So as you can see here, this one is input. The range goes from negative infinity to the positive infinity, but the output goes from 0 to 1. And if the output is greater than 0.5, then we can say this belongs to class 1. Otherwise, it belongs to the class 0. Okay, this is binary classification. Okay, and then what about the multi-classes? So we can apply multinomial logistic regression. Maybe you might have heard about the softmax from deep learning or neural networks. Okay, so when we have a many classes, then we use a softmax. Okay, in this case, we are interested in the probability of y when y is c. And that can be computed in this way. So this one is exponential function, and this one is a linear equation like this. Or this could be a neural network with many layers. So this one is the target class. And these ones are about all the classes. Okay, then we can understand this logistic regression from a probabilistic view. Okay, so given a class conditional density like this, so this one is actually a likelihood, right? So when we assume that the class is k, then what is the probability of x? How likely x is coming from class k? That is this probability, this likelihood. And we have a prior. Without any information, we can have some distribution. And for binary class, okay, this is a posterior. Okay, then it says what is the probability of class 1 for this x. Then we apply the base rule here. And this one is a likelihood. As I said, this is the probability of x, which is coming from class 1. And this one is prior probability for class 1. And this one is exactly the same as this one, and this one is for class 2. So this is simple base rule, and we can define a of x in this way. Then this whole equation can be rewritten in this way, and this is actually a sigmoid function like this. So we can understand this logistic regression from probabilistic perspective. Okay, so there is a strong connection, direct connection actually here. This a of x is called logit function. So we're going to talk about this issue in the neural network chapter. But basically when we have a neural network, then we have output, and this A of x is corresponding to these outputs. And then we have to apply the softmax to this output. That's how we calculate the probability for the classes. And for multiple classes, we do the same thing here. So we are interested in class K, and then this is target class, and we need a summation over all the classes. If we define a sub k of x in this way, then this whole equation can be rewritten in this way. This one is a softmax. So when we use a softmax, this softmax is actually corresponding to this probability when we assume this. And this equation can be approximated or implemented by a linear function of x or a neural network with many layers. Okay. Now we know what logistic regression is, and now we want to talk about what is the objective function and how can we train the model, the parameters. Okay, so for a linear regression, the objective function is an error function. Okay, like a root mean square error or something, and with the Gaussian noise model. Okay, so that's about the linear regression. But as I said, the logistic regression is about the probability, right? So instead of minimizing error in linear regression, in logistic regression, we want to maximize likelihood. Okay. So we talked about this likelihood a long time ago. So that is actually coming back here. So let's assume that we have two classes, and then the probability of t given x is given by this. T is the label and the y is the estimate. Then when t is 1, then this probability is y. Okay. And when t is 0, then this probability is 1 minus y. So either y or 1 minus y. This is what it does. Only for the binary class problem. And then when we have a multi-class problem, then the p of t given x is actually multiplication of this, the product of y to the power of t. So if you look at this one is actually the same as this one. So look at this one. We have C classes, and then only one class has 1 and all the others are 0. So it looks like 0, 0, 1, 0, 0, 0, 0 when we have 7 classes, or 0, 0, 0, 1, 0, 0, 0, something like that. If the target class is the 6th class, then it should be 0, 0, 0, 0, 1, 0, something like this. Okay. And then y sub k is the estimate of the model. So y sub k is something like y sub 1 and y sub 2 and y sub 7. And then we have a superscript here. And if the target is the 6th class, then y sub 1 to the power of 0 is 1, and the y sub 2 to the power of 0 is 1, and all the other ones will be 1. And how about this one? Y sub k to the power of this one is y sub 6. Okay, and then if we multiply all these probability, then we have y6. Okay, so this one will be y1 if the target class is 1, the first class, or this could be y2 if the target class is the second class, etc. So this is our probability. Okay. Then we can actually use the likelihood. But since we are interested in minimizing, so we have a negative, and the likelihood is based on some exponential function, so we take a log function. So that's why we have negative log likelihood, or NLL. Okay, and the likelihood is defined as follows. For binary class problem, and we have n samples. Okay, this is likelihood. We actually talked in the previous slide. And since we have n samples, and assuming that the samples are independent, okay, that's reasonable assumption. So we simply multiply all this likelihood, okay, and then this one we can rewrite this probability with this equation. We just saw this one in the previous slide. This is our likelihood for the binary class problem. And when it is multi-class problem, then we saw this one in the previous slide, and then we just multiply this probability for all the samples. This is likelihood for multi-class problem. And then, as I said, we will take a negative log likelihood. And then if we take negative log function to this, then we get this one. And if we take a log here and then negative, then we get this one. This is our objective function. Okay, again, these are the labels, and y sub I is estimate. Estimate means, based on the model parameters, we get this one. So in this variable we have actually lots of parameters. Okay, so we have to change this value to minimize this negative log likelihood. That's how we update the parameters. And we're gonna use gradient descent method or Newton method. So we're gonna talk about all this training method in optimization chapter. But anyway, this is our objective function.